Hi, everybody, and welcome to Physics 10. Today is May 25th, and today we'll be covering the last chapters basically on this class, namely relativity. So we are toward the beginning of the 20th century, basically around 1905, 08, when the first theory came out. And then for Einstein, and the second theory came out around 1915. And there was the matter with big time with the laws of physics at that time. So we needed something to basically understand what's going on. So before I do that, let me mention what's coming in terms of other assignments and stuff like that. So the biggest deal is we still have the exam, which is due, the final exam, which is on June 8th. Okay, June 8th. That's a Tuesday, actually. And that is how it was posted on the syllabus a long time ago when we first met, June 8th. Now, the final review, for some reason, needed to be fixed, because right now it says June 8th. It cannot be June 8th because that's where the final is. So I have to fix that. That should be June 7th when it's due. And June 7th is actually a Monday. So let me fix that quickly because okay, so actually in the announcement it says that. So let me go back into the models. So again, the review is graded as participation, and it has 236 questions basically in it. The actual exam itself has about 90 questions. So that's really the last exam for this class. So hopefully, guys, you'll take the time. It should be available. The review should be available this Friday for you guys. Since this is the last class, basically, we will not have any more meetings, at least scheduled meetings. But if you guys feel like you have a question or something, please feel free to send it to me. I'll be more than happy to answer it if I can answer it short answer, like via message through Canvas. Or if need be, we can meet. We still have time where we can meet on Thursday and Tuesday. The regular time is basically where we're supposed to be meeting anyway. But we don't restrict ourselves to those times. So if there is another time that works better for you, please let me know, and I will check my schedule to see if it's available. Then we can meet during that time. Now, if it's something that interests only you, that's fine. We can talk about it and hopefully we resolve it, and there will be no issues after that. But if it's something that benefits the entire class, so what I propose to do then in this case is, and I will tell you upfront, to record that point, that section of it, okay? So you will know that I'm going to be recording this section. And then after we're done, I'm going to basically post that for the benefit of everybody else. So this is the only thing that I basically still have. Again, we have quite a few assignments. I know some of you did not turn them in, so please take care of them. And if you have difficulty with them, please let me know so that we can get these things done. I think there is an assignment due the 29th, which is this Saturday. So take care of those. And if I did not grade it, you can still submit it. Okay, so that is basically the rule of thumb that we go with. So this is in terms of what we have in general, what the course is headed to, and where we are. So since we have plenty of time for those questions, please feel free to send them. I'll respond to you. If not, we meet. So let's jump into the lecture today. So let me share with you the screen, share. Okay. So where is this thing in here? Let me move it closer in here so that you can see this and move this one in there. So we're talking about the theory of relativity of Albert Einstein. As I was saying, there was something the matter with a few things. One of them in terms of intuitive things, okay? What we used to think that, for example, if you are jogging on a train that is going 50 miles per hour and you're running in the same direction where the train is going, let's say, for example, 5 miles per hour, then intuitively, we know that your velocity with respect to somebody standing on the station is going to be the sum of the two velocities. You're 50 miles per hour plus that of the train. I mean, the train is 50 miles per hour plus that of your velocity with respect to the train. So in this case, your relative velocity is 55 miles per hour. I mean, you can, if you have had a chance to go into an airport, you can see on those runway, those things that have people walk, basically, there is a belt in there that is running with basically a little bit of a jog for a normal person. If a person is walking on it, he or she appears to be even running or going super fast. And that is because of our intuitive notion, and actually that's how the velocity is at. There was experiments that were done before, trying to determine, for example, the speed of the Earth with respect of the ether. So, and then also other experiments similar to that, trying to determine the speed of a source of light, and as the source is moving. With light, this seems to break. So if you're moving with your car, for example, let's say 100 miles per hour, give it a high speed. I know, don't do that, okay? You're gonna get a ticket no matter where you are. So we're getting super fast with your speed, and let's say we have an extremely sensitive piece of equipment that can help us determine the speed of light. Whether you're sitting still and basically you have the light on, or you're moving super fast and have your light also on, both speeds register the same speed for the speed of light. So it seems like the speed of light has nothing to do with the source. So that breaks something that we know from old mechanics, from Galilean, from Newtonian mechanics, which rests on the Galilean, relativity. The one that I described first, the fact that you have running at 5 miles per hour in a train 50 miles per hour for a total of 55 miles per hour. That is actually what is known as the Galilean relativity, because that's the velocities add up simply in that. This does not seem to be the case when velocities are of extreme high values. Even if you are running 99% the speed of light, in a frame that is running also still 99% the speed of light. So in this case, you expect your speed to be almost twice the speed of light with respect to an observer observing you. No, it's not going to be that. It's going to be very close from the speed of light, but it never is going to be equal to it. So it's going to be probably 0.99999, the speed of light, but it's never going to exceed that value. So there seems to be a problem with classical mechanics. So we needed to have a better understanding of what's going on. So Mr. Einstein came up with two postulates. First of all, he stated that physics should not matter. If an object falls with respect to this observer, is going to fall with respect to another observer. If this observer determined that it's going to fall, the other observer also would determine to fall. So the outcome of the experiment should be the same no matter what. So regardless of which one is observer, whether you're sitting in the station or whether you're moving in the train, the fact that an object fell is a fact for both observers. So this is postulate number one. The laws of physics are true for all observers. Okay, that's one. The second postulate he postulated is that the speed of light has to be constant for all observers, and it's the same value, c. As a consequence of the second postulate, not a single material can travel with the speed of light. The only object that can travel with the speed of light is light itself, or any massless, any object that does not have a rest mass, that does not have a mass by itself, that can travel with the speed of light. Like, for example, gravity waves. Those they can travel with the speed of light, but because they don't have mass. But anything else that has finite mass, they cannot reach the speed of light. So this is basically as a consequence of that. Then there was some weird stuff that started to appear then. One of them, if you want to keep the speed of light the same, and if we don't agree on the ruler, because the speed of light has to be the same, but I am moving. So in this case, the way I measure distances is different the way that you measure distances. As a consequence of that too, the time also has to change between the two observers. So we have some weird phenomenon. We have to have the time dilation and length contraction. In other words, we don't agree on the measurements devices themselves, basically, and that becomes a problem. Because at the end, we have to agree on only one thing, which is the speed of light being the same. So our rulers and our clocks basically shift things, and this leads to all kinds of problems. One of them, for example, is an event that is simultaneous for an observer. Let's say, for example, I'm sitting in a train, and throw two objects in the opposite directions, okay? For me, the train is stationary. Basically, it's not moving, okay? Because I'm sitting on it and the train is moving. So I'm sitting actually, and I can sip my coffee because at that point, this is my rest frame. For the observer who's in the station, that is not true. The train is moving actually. So his rest frame is that of the station. So in this case, if I throw two objects in the opposite directions of the car that I'm sitting in, then both of them will reach the ends in the same time if both of them are flying with the same speeds with respect to me. Then in this case, this is a simultaneous event that when they hit the window or they hit the sides of the train, since I'm sitting right smack in the middle, then these are two events that happen in the same time. So this is simultaneity. However, for an observer looking at outside, he or she must calculate the speed slightly different. First of all, the train is moving one way. So the ball that is moving in that direction is basically its velocity is less by the relative velocity. If the train was moving 50 miles per hour, and for an observer, that is basically looking at it outside, it's also 55 miles per hour, so it's like the difference of them. It's like, for example, you're sitting on you're driving on the freeway, and you're going 50 miles per hour, and the person next to you driving 50 miles per hour. For you and him, with the other driver, you're basically driving in the same time, so you're in the same speed. But if he or she starts to move faster, let's say, for example, going 55 miles per hour, of course, he or she will gain velocity over you because you stay at 50 miles per hour and they start gaining velocity. So in this case, it's the difference, actually. So because the train is moving 50 miles per hour and you throw a rock, for example, at 5 miles per hour, so the actual speed in this case is 45 miles per hour. So it's going to reach the end after the one that went on the opposite direction. The one that went on the opposite direction is moving 5 miles per hour, and the train is coming to meet it at 50 miles per hour. So in effective, in this case, the relative velocity is actually 55 miles per hour. So in this case, the one that you throw in the back, because the train is coming towards it, at least from the vantage point of the observer outside, will happen first, and then later, the other event happen where the ball going forward also will hit the other side of the train. So simultaneity for me, two events that happen in the same time, is not simultaneous in another reference frame. This is all kinds of things that started to come up with. Another paradox that comes in is the twin paradox. The twin paradox has to do with also the speed of light, because of the time basically dilation for the observer outside. If you have two twins, let's say, for example, both of them are 20 years old, you have to think that although a lot of these things are thought experiments, but actually if you measure the clocks and they were measured, they actually, all of these are facts. They are not actually hypothetical. Of course, we didn't do the twin experiment because, first of all, we don't have a spaceship that travel with the almost speed of light. But if we do, here is the scenario. You have two twins, basically a twin, that both of them are the age of 20. And for example, one of them travels to a nearby star and comes back, going with the almost speed of light. During that time, that person, the proper time, is whatever time it takes for him or her to go there, because they're moving super fast, the time moves extremely slow for them. Versus the other brother, let's say, for example, the time it goes back and forth for light is about, let's say, Proxima Centauri, it's about 4 light years from here. So 4 light years going up, 4 light years coming down. He's traveling with almost the speed of light. So we're going to assume it takes about almost 8 years for him or her to go back and forth. That is with respect to the brother who's sitting in here. That person will age to become 28 years old. Whereas the other one, probably he or she, depending on how fast he was going, probably 22 or 23. Now they age differently because of the time dilation. So this is all kinds of paradoxes that seem to defy our common daily experiences, and that is basically what relativity brought to us. But these are facts. I mean, your GPS on your phone does not work without this phenomenon. Clocks slow down away from the, closer to the Earth, then further away from the Earth. And we always have to do that. I mean, for the satellites, for the GPS satellites, we have to always make these corrections. Otherwise, we will have all kinds of wrong positioning things and problems all about. So in other words, these are real facts, are not actually hypothetical things. In other words, this theory is actually very, very accurate, much more accurate than classical mechanics. And classical mechanics turn out just to be an approximation of it. Another consequence of it is also, and this is a big deal, is that the energy and the mass are the same thing with the only thing that is different is that the constant c squared to be more specific. So if you have 1 gram of matter, you really have an amount of energy. So the mass and energy are equivalent to one another. And this has immediate consequences because it helped us understand what's going on in the sun and the stars in general. How do they get their energies? And again, because of this, Heinz Bethe actually proposed the process through which energy is converted inside the stars and basically nuclear physics and all kinds of things. And the correspondence principle at the end between classical mechanics and relativity. I'm sorry. So we'll get into it later on. Anyway, the point being in here is we have also general relativity took those very same ideas and actually generalized them in terms of the gravity versus acceleration. That an accelerated frame will behave exactly like gravity. So because now we are not dealing actually with motion at constant speed, but motion with acceleration. And that was able to predict a lot of things. One of them is gravity waves, which Einstein basically predicted that they will never be able to be discovered because of the fact that they are so faint. But sure enough, we started discovering them with the LIGO projects, for example. We have seen them. And also the other thing that was predicted by this theory are black holes, which Einstein thought that they are too weird to exist. He dismissed them. These are two freak things in nature that they should not exist because they are too much of a problem. Even neutron stars were a problem for his taste. He didn't like them. But at the end, they turned out to be real things and they were observed and measured. And one of them is the black hole M87. That was, we took pictures of it. I mean, that was in 2017. So that is really two of the consequences. So this stuff is real. Another thing that is actually a consequence of this theory is the gravitational lensing. And that was verified in the time of Einstein. In 1919, there was a solar eclipse that the sun was basically hidden by the moon. Then the day became night and the stars on the other side of the sun, you can see them. Some of the stars you can see, they were supposed to be in a specific location in the sky, but they appear to be in a different location in the sky, and that is because of the gravitational lensing, which is actually that light bends around heavy objects, supermassive objects like the sun. And that was actually a consequence of relativity that Einstein predicted, and it was confirmed actually in 1919 when he was confronted with these observations. He said, well, I was confident in my theory. It would have been big. I mean, God would have missed on a lot if we did not really have relativity in that sense. So it seems like there are a lot of things in here that are true about this theory, and it is actually beautiful and accurate and everything else. Now, before I start actually the slides, let me say something about it and quantum mechanics. Quantum mechanics is actually a very accurate and beautiful theory too. And relativity is actually a very beautiful and accurate theory too, but both of them are fundamentally basically exclusive of one another. One of them is probabilistic, namely quantum mechanics, whereas the other one is deterministic, namely relativity, in the sense that if you give me the conditions now, with the relativity, I can tell you what's going to happen later if I'm clever enough to solve the equation. So the solution, relativity is deterministic. In other words, it predicts. There is a 100% prediction based on it. There is no probability whatsoever. I mean, the errors that you make are just errors in calculations or errors in measurements, and that's typical of any measurement. But the theory itself is deterministic, whereas quantum mechanics is inherently probabilistic in a sense that if you know now what's going on, let's say, for example, you measured some property, it doesn't matter, the spin, the mass, the energy, whatever, the kinetic, or the momentum or anything like that, you can only, if you know the state now, basically, of a system, you can only predict a probability of it being at some state later on. You cannot tell if it's going to evolve there. You will only have a probability of it. And this has nothing to do with measurements. It has nothing to do with the lack of calculations or errors or not being able to. The theory itself is inherently probabilistic in a sense that the only thing it can yield are probability densities, that's all. So there is this fundamental difference between the two, yet both of them, they meet only with one thing. When things are they were extremely small, and then you start to make them bigger and bigger, at the end you recover classical mechanics, the one that we started with way back, Newton's mechanics. That is from quantum mechanics to Newtonian mechanics. Also, when things are supermassive or super fast, when you slow that down a little or make their masses smaller, they also you recover classical mechanics, namely Newtonian mechanics. So Newtonian mechanics is, if you wish, an approximation for one and an approximation for the other. And it works beautifully on a daily basis because we don't deal on a daily basis with supermassive black hole objects or supermassive stuff, or we don't deal with super fast objects on one hand, and we don't deal with the electrons, protons, at least on a daily experience for our cars and things like that, that we use F equals to ma, and it works beautifully. So these two, although both of them are accurate and beautiful and everything, and they're fundamentally contradictory to one another, and physicists around the world are trying to unify them, and this is actually the holy grail of physicists, trying to come into some consensus between the two, but they seem to be they seem to be opposite to one another, and describing what they describe beautifully and accurately. So this is just a statement I wanted to say up front about the two sciences, the ones that we've been exploring so far. Anyway, so let's get going now. So motion is relative. In other words, what you think is stationary is just basically a perspective only. The fact that you and I have been sitting in here is not really stationary at all. Everything is moving, including us in here, because our reference frame, which is the Earth, is spinning. And the Earth is actually going around the sun with a certain speed. The sun itself is going around the galaxy, and the galaxy is drifting with all of the other galaxies in a local group to one direction, and maybe the entire universe is spinning and everything else is in motion. The atoms in motion, so everything is really in motion. So the fact that we have stationary is just a perspective. This is the experiment of Michelson and Morley that I was talking about, and here trying to determine, for example, the relative speed, for example, of light with respect to Earth. Earth is moving, I know that, you know that, Earth is spinning. So if you orient this beam, so this is the light source, and if you send the light source, let's say, for example, the Earth is moving in this direction, okay? So the light that goes straight out, this is actually a semi-transparent mirror, meaning half of the rays will go straight through, and the other half will be reflected. So now they hit a reflector in here. Both of them are perfectly reflective mirrors, those two mirrors, and the light bounced back. So the light bounced back in here. This distance and this distance are the same. So if this is actually a clear glass in here to adjust if there is a delay between the two, okay? To make sure I don't have interference in here, I have constructive interference in here. So what happened in here is that the light, that doesn't matter which way you orient it, both beams arrive in the same point at the same time, meaning that light travels with the same speed, doesn't matter, in the same direction of the Earth or perpendicular to the direction of the Earth. So if you add the speed of light to the speed of the Earth, you're not going to get anything more than the speed of light. End of the story. That was really something that was a revelation in here. Okay, so this is the same explanation as I was talking about. This is the same argument as I was talking about in here. Whether you're traveling toward the light, so in this case, you expect if this one is moving towards you, theoretically, it's the speed of light plus the velocity of the source. But that's not true. The speed of light that you record is the same thing. If it's receding from you, the same thing. The speed of light is the speed of light. So you expect it to be slower because it's moving away. If you are moving towards it and it's coming towards you, which double the speeds now, it's still the same value. So speed of light is constant, and this is observation. Okay, so Einstein made it into a postulate. So this is the simultaneity, two events simultaneous. And this is the experiment as I was describing. For example, if you have light traveling in both directions in here, so expect in here one event to happen before to happen at the same time because the speed, but in here they are different. So again, simultaneity starts to break down now, but the speed of light is the same for all observers. So this is the problem with the clocks now, since we want C to be the same thing and measurement devices. So space, if the ruler, for example, because we have to change the reference frames now, because the distances appear to be different in here, because this distance appears to be shrunk compared to the other distance, which said actually this one appears to be shrunk and this one has elongated because it takes like more time to reach this end. So now because this distance has elongated in one direction, time also has to adjust for it so that the ratio has to be the same. So this is basically what this means in here. So if we do a transformation, we have to do it in such a way that this ratio is the same. Okay? There was a mathematician in the time of Einstein, and that mathematician actually was Mr. Lorentz, actually a physicist too. He came up with some beautiful physics forces and things like that. So he did actually the transformations that now bear his name. So again, this is the time dilation. If you have a clock that ticks between two mirrors, for example, it goes up and down, let's say in 1 second. So this mirror must be 300,000 kilometers apart, or fraction of a second, and you adjust the clock accordingly. So if this is the time it takes back and forth, now, if this were to move in a reference frame for the observer, he measures the time up and down, and he found exactly the time it takes for it to go up and down. For the observer looking at outside, the ship is moving. So the path for this object is going like this. So it's much longer, this path, than this path for this observer. So this is basically since this path is clearly longer, so the time in here that needs to account for it must be actually longer for this observer, okay? So that the ratio is the same, because this is a zigzag pattern. This observer now, that the time is going up and the path is going up and down, so it's a shorter distance. So the time for him is also shorter in this case, okay? So this is basically the idea behind the time dilation and the length contraction in here. So the time must have to go slower in here, and the distance has to shrunk in here to make the ratio the same. So again, this is the same idea as before. So the distance, the speed of light is the same in here. So if you increase the distance, you better increase the time with it so that you keep the ratio the same. Mathematically, as I was saying, this is actually the gamma factor, the Lorentz factor also called. This is what needs to be done to fix everything in here. So mathematically, you write T equals to gamma T naught, where T naught is the proper time, the time for this observer in here, up and down. And this is the time for the observer outside. Gamma is a factor that is always greater than 1. When V is equal to 0, square root of 1 is 1. When V is very, 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 very large, almost the speed of light, you have 1 minus almost 1, which makes this difference extremely small. But when you divide with something that is extremely small, the number gamma is going to be more than 1. Far more than 1. So when gamma approaches infinity, becomes extremely large, you have almost hit the wall in here. You are almost with the speed of light. So this is how the behavior of gamma is. So the gamma factor for most of our daily experience is 1, because V practically is 0 compared to the speed of light. The fastest object we made is going 40,000 kilometers per hour. And that is super small. When you divide that 40,000 kilometers by 3,600, you will find how much speed you're going to get. What is 40,000 divided by 40,000 divided by, it's going to be almost basically 1,000. 3,600. No, it's actually 11 kilometers per, yeah, I mean, when you multiply it by meters. So it's 11 kilometers per second. 11 kilometers per second is nothing compared to 300,000 kilometers per second. So you have 11 divided by 300,000. When you square it, it's going to be practically 0. So in our daily experience, the fastest thing that we built cannot be outside of this region at all. It's not even a quarter of C. It's practically this region. So that's why our daily experience do not distinguish this thing. We don't see this factor in here, gamma, at all, based on our daily experience. Because all we live in is a world where, at least on a daily experience, around this value in here. But for particles that are moving super fast in nuclear accelerators or cosmic radiation or things like that, they could be significantly in this region where gamma is very large. Like, for example, the mu1, which is a elementary particle that is produced in the upper atmosphere coming from the radiation of the cosmic radiation. So it's created in the upper atmosphere, and it travels all the way to the laboratory down on the Earth, and they're actually underground to be detected. Its lifetime is only supposed to be 2.6 times 10 to the negative 6 seconds. Even if it was traveling with the speed of light, and it cannot because it has a finite mass, then the maximum it can go is about 600 meters. Yet it goes from the upper atmosphere down to the ground several kilometers, dozens of kilometers before it decays. So what happened in here? Well, the time for it seems to have extended. It's moving basically more. It had lived more than 2.6, according to our calculations, should have been lived more than 2.6 microseconds or 10 to the negative seconds. So this is an observed fact. You ask, okay, what is the perspective of the mu1? If you are, for example, sitting on the mu1 and coming down and it's just been created. Well, in this case, your life is your life, 2.6 microseconds, 2.6 microseconds. For you, you are sitting in this here. You are sitting in here. For you, the mu1 has lived only 2.6 microseconds. So what happened then in this case is the length that you thought is 10 kilometers from the upper atmosphere to the ground in here has actually shrunk to be less than 600 meters. For it, it's seeing that, oh, this distance is less than that. No time, no problem. So it's made that distance. So this is actually the time dilation for ourselves in here. We measured 10 kilometers, but for it, it sees only the 600 meters, okay, 0.6 kilometers, smaller fraction. So these are all the stuff that is coming from let me see if I have a picture of that. I'm going to share with you a personal picture with me and my students when we went actually to a nuclear if I find the picture, of course. Hold on. And I don't find the picture. What is the... I'm trying to find a picture in here to share with you when we went to a... oh, wow. Here it is. So let me stop share and share with you. We went to the Fermi lab, nuclear reactor. Fermi lab, it's not a nuclear reactor, it's a lab to detect elementary particles. And actually they work with neutrinos, they detect neutrinos. This big thing that you see in here, this big circle is actually the accelerator of the particles that they study. And they study cosmic radiation and radiation coming from other places. So we were looking at it. On top here is me next to the Feynman diagram, and my other students next to the Feynman diagram, and this are all the detectors for the detection of the neutrinos, which are actually one of the byproducts of the decay of the muon, the particle that I was describing. So again, it's fun stuff when you see it firsthand, okay? When you see what people do on these things in here. So we went to Chicago in Fermi Lab and visited it. That was in 2017, I believe. Yeah, 2017. So this is actually first-hand account from what people are measuring in there, okay? About the muon story and how it sees things more than it should be and less and so on and so forth. Anyway, so this is the twin paradox. I mentioned that the fact that two twins, they leave, one of them comes in, the one who traveled back and forth comes in and find his twin brother, basically in this case has aged extensively. Now, again, it has to do in this case with the time dilation, and You may ask again, and this question is a common question here for the twin paradox that people get confused about it, is from the vantage point of the twin brother who traveled. He's sitting in his station, he's not moving. So because we always discuss it from the vantage point of the staying brother, the brother who stayed in here with the blue shirt. That brother is not moving, he's sitting on the earth. And his brother traveled with almost the speed of light, and when he came back, he found his brother basically an old man. So why wouldn't we say that, okay, this brother who traveled with the light blue color stuff in here, why? See, he's sitting in his station, so he sees back, he looks back and he sees the earth moving away with his relative speed, which is super fast. So he should think when he comes back that his brother will stay young and he himself will age. Well, there is a problem with this argument in here. It's not exactly 100% equivalent, because the brother who traveled accelerated to gain that speed and had to stop and return back, basically decelerate and accelerate back and slow down again to meet his brother in here. The one who's sitting here has not accelerated, and this makes the difference between them. So this we can determine who actually aged and who did not age. The one who experienced the acceleration in this case must be the one moving versus the one who stayed stationary because he did not accelerate. So that's why we know the brother who stayed in here aged versus the brother who came back. So there are a lot of paradoxes like this one's in here in relativity that you can only find them when you think about it. Again, this is how they traveled, and basically they looked into one another and came back and so on and so forth. So this is the paradox. By the way, all of this stuff is part of the exam, okay? So do not miss these things, okay? Chapters 19 through 36, all of them are part of the exam that is coming down. So again, you can go through the calculations and the numbers and you should be able to find the idea behind it. So this is the twin paradox. There is another paradox that you will find that, out there. It's called the too tall to fit. Sometimes called the ladder paradox. The ladder paradox is basically you have a ladder that is bigger than a barn. Well, how can you fit a ladder that is bigger, longer than a barn? Basically, if the ladder is moving super fast, it's going to shrink in length just enough for it to fit in the barn. Well, you could argue from the vantage point of the ladder is sitting still. It's actually the barn that is moving towards it. So it's a barn that should shrink in size, okay? So when the barn shrinks in size, it's going to even be smaller for the ladder to fit in. Well, here is the problem with that. Simultaneity should need to be taken into account. Well, when we consider in the rest frame of the ladder or the barn that the ladder fit in it is because the front and the back also are in the same time in here. But when we are in the moving frame in here, that simultaneity is broken. So in this case, the back of the ladder will go in before the front, and that's how we fit it in. Simultaneity fixes the problem. So a lot of these things happen to be can be resolved with basically these arguments. Relativity can be confusing and at times can be a little bit hard to understand, but it's really all of these things that need to be taken into account, or everything, to be able to answer it. I leave the discussions for you guys to be able to go through it. This is basically the point that I was talking about. This is the everyday experience. The velocities add, whereas the relativity, they add up in a different fashion. The speed of light comes into play. And if I make V1 equals to C, this will be C plus V2, and this will be 1 plus C over C cancels, C over C squared cancels, so we'll have V2 over C. And if you carry the algebra a little bit, you will find the velocity is still C. Make any of these two V's C, and the value is going to be C. Let's make both of them C. This one is C and this one is C. This is 2C, clearly. C plus C is 2C. And in here you have 1 plus C times C is C squared. Divided by C squared is 1. 1 plus 1 is 2. So you have 2C in the numerator and 2C in the denominator, and the 2 cancels the 2. So even if you add a C and a C, you're going to get a C. Isn't this fascinating? Even algebraically, this fits the bill. Whereas in here, if I have one light going with the speed of light and another one going with the speed of light, the source is going with the speed of light, C plus C is 2C. And this is not true based on the observations. This is true. When you add a C and a C, you end up with a C. You cannot end up with a 2C, because clearly you put a C and a C, that's 2C, and this will become a 2, and a 2 cancels the 2. So when you add 2 C's, you end up with a C. This one does not. This will give you a 2C, actually, straight out. And this is not true. This contradicts observations. This one meets the observation. This is what Michelson and Morley and other people have observed later on. So this is the length contraction I've been mentioning in here. When objects appear to be moving a lot super fast, their length shrinks by this 1 over gamma. This factor is exactly 1 over gamma. Remember, gamma is more than 1. So 1 over gamma is less than 1. And this is basically what happened in here. And when you move with the speed of light, you will have no length, basically. This is not an illusion, by the way. This is a real thing. So depending on the perspective, of course. So again, the momentum, we used to call it mass times velocity. Now we have to introduce gamma to it. Actually, the whole thing becomes a little bit more corrected this way, including the dynamics in a sense, okay? Because gamma is more than 1, of course, you will have more momentum in this case. There is another way of looking at it to say gamma m has actually changed. The mass has actually changed because of the motion. This led to this result. As I was saying in the intro, this is E equal to mc squared. This is a common, basically, signature to wherever you see it that is referring to relativity. Mass and energy are equivalent according to relativity, okay? And this can be used to convert energy in any form. It's just mass, whether a chemical process or a nuclear process or understanding what's going on inside the sun. Without this equation, we had no clue what's going on inside the sun, because there was not enough chemical processes to understand how the energy gets its, how the sun gets its energy. But when we put this one in perspective, when Hans Bethe had suggested the process based on this equation in 1930s, it became clear, and then later on it was confirmed in observation. That's exactly what's going on inside the sun, and this is what we think is inside all of the stars, not just the sun. So again, I mentioned for everyday experience, V is so small that gamma is practically 1. But for large values, gamma becomes more than 1. Again, the length, there is no length contraction, and the momentum is just mv. So everything is works fine with classical mechanics, okay? We recover classical mechanics from relativity if we do the proper adjustments. Again, the general theory of relativity resides on those postulates, plus another postulate in here that there is no way for me to tell if a reference frame is under a force of gravity or accelerated frames. Both of them are the same. And let's explain how that works, okay? This is a person who's not accelerated. If you're not accelerated, you have no weight. There is no problem with that. So you say, in this case, I have no acceleration or I have no weight. It's the same thing. You don't feel anything. You feel weightless. Now, if you stand on a scale and you're accelerated, the scale now reads a number. For you, you don't see what's going outside. You're sitting inside the capsule. So you think everything is all well. So you say, okay, there is a force that pulls me down to the ground, and I call this force gravity. So this is my interpretation of what's going on. And as a matter of fact, I can measure this force of gravity. If I stand on a scale, the scale will push back on me, and that is the reading I'm reading in that. So in here, the two may be confused with one another. So that is the principle, one of the principles of a general theory of relativity, and it led to a lot of wonderful results. Let's look at another experiment. If I take this mass in here and I drop it, I can say the reason why it fell down because it has weight. And if I let go of it, because the reason why it's not falling right now is because I'm holding it. So I'm countering the weight. But if I let go of it, it's because of its weight. And I give it a value, which is mg. There is no reason for me not to suspect that what's going on in here is actually the Earth is coming to Russia, accelerated towards it, and it's the same thing, the same observation. So that too could lead to the same result, okay? If you are sitting on a frame that is accelerated, for them, the masses are not moving. They are still in their places. It's the reference frame that is moving upward. Since I associate that with my own weight, I'm going to assume that those masses actually has a weight too. And that leads to the same result. Actually, this goes further with a lot of other observations, like, for example, the projectile motion. If I send a bullet straight through, the bullet is just going straight through. But for me, if I'm sitting in the spaceship, I can say, oh, what's going on in here? The path is going like this because it started in here on this line and it hit in the bottom in here, way away from that line. So it went through a projectile motion. So again, that weight can explain the projectile motion and give me the bending basically of this object under the gravity. But for an outside observer looking at this one, all he sees is that the bullet is moving straight through. What's going on is the reference frame is moving upward. So this is basically one of the fundamental principles in here. This could be not a bullet, actually, it could be light too. The light will bend under gravity as it does under acceleration in here. So this is my interpretation, is there is some gravity, but for somebody else, it's just an accelerated frame. So that is basically the equivalence of the two in here. So the same thing in here for light. So the bending under gravity and under acceleration is the same thing. So you have a supermassive object, it can bend light. This is one of the predictions basically of the theory of relativity, the general theory of relativity. And as I was saying, in 1919, it was actually observed. And now you can confirm it with a huge gravitational lensing. That is one of the biggest things that you can see a whole galaxy behind another galaxy, and you see the whole galaxy or behind another massive object that is like a black hole, for example, and you see the stars around it forming a big ring. If you have seen the movie Interstellar, you see basically the light doing all of that shadow thing in there because it's actually bending. It's from a source behind the black hole. So if there is a source behind the black hole, the light actually gives it that corona basically shape in there. So the same thing in here. In 1919, like I was saying, the star is expected to be here, but it was apparently looking in there. So the light bent as if I have a refraction on a surface in here of between water and the ground. So this is like a lens, for example, works exactly like the lens that it bends light in here. So that is actually the same phenomenon. That's why it's called gravitational lensing, because it acts like a lens. So this is one of the consequences, because light also bends as much as matter bends also under the effects of gravity, because the same things are true in it. So again, gravitational inside a well also have this experience in here. And as I was saying, Mr. Einstein basically said, okay, he was not surprised. He thought that it has to be true. I mean, the theory is beautiful, so it should be correct. And beauty sometimes is an argument in physics for physicists, okay? Although some physicists know they reject that argument altogether. Another phenomenon I mentioned that in the intro is the time dilation. And clocks near the surface of the Earth appear to tick slower than the clocks appear move further away. And that the only thing that is different is the gravity is stronger near the Earth than further away from the Earth gravity. And as I was saying, the GPS system, because it usually uses satellites that are far away, needs to really take this phenomenon into account. Otherwise, we will not have accuracy of GPS systems on the Earth. So this is a real deal. It's not something that is hypothetical. Okay. And again, because they appear slower in here, because they're moving faster actually now in here. So this is accelerated versus this one in here. So this clock will appear slower. Remember this, the acceleration is v squared over r. An object that is sitting in here is not accelerated at all. An object that is in here is accelerated. So you detect the same thing, whether you are under the effect of gravity. So heavier gravity will slow down the clock, or more accelerated systems will slow down the clock. So both of them are the same thing. So again, this is should measure slower than a clock on the Earth. As a matter of fact, if you are near a black hole, the time will come to almost stand still. Okay. So this is one of the things that. One of the problems that actually, one of the immediate success of the theory of Einstein for general theory of relativity was the path of Mercury. The path of the other planets was described beautifully by the work of Mr. Newton, where he basically had an explanation for the theory, for the work of Mr. Kepler, for how the planets go around the sun. So there was no problem with that. All the planets have those elliptical paths. And the elliptical paths, they have eccentricity, and based on the eccentricity and the energy, you can have beautiful predictions for all of the planets. The problem was Mercury. Mercury has a precession, okay, around the sun. So people said, okay, let's make corrections on this. Let's take the effects of Venus, because Venus is nearby, and you make corrections based on Venus. Let's take Earth effects. Let's take Jupiter, which is the supermassive object. But no matter what, there was a fraction of a degree that is always wrong. No matter how much correction you end, you cannot basically match the theory with the observations for the path of Mercury. And that was a nagging issue for a lot of people, including Einstein himself. And at the end, when he worked out the algebra for the path of Mercury, that precession was beautifully explained. Okay, so that was the first success, actually, of Einstein. Again, if what the theory does explains something that was observed before, that is not good enough. That's why people, when he came up with that explanation, yeah, that's good. I mean, we could have come up with a different explanation. If all you do is explain something that was observed already, that is not good enough in the theory. I mean, it's good, but not good enough in a sense to come and replace everything that was done before. It has to match with everything that was observed before, and including this observation that was done for Mercury. One of the immediate telltales that this science is actually accurate is, as I was saying, the 1919 observation of the gravitational lensing during the solar eclipse. That was something that was predicted by the theory, never observed before, and now is confirming the actual theory. So the fact that Mr. Einstein explained the path of Mercury, that was good. But it was not good enough for the theory to take hold, actually, and become acceptable in the general community until something else really comes up to confirm it. One of its predictions was this thing, that you should observe gravitational lensing. So sure enough, it was observed. See how the dynamics work? Same thing with Mr. Newton. When Mr. Newton came up with an explanation for the path of the planets around the sun, based on the work of Mr. Kepler, that was good enough. I mean, that's fine. I mean, you just explained something that we have seen before. What can you tell us more? Well, when Halley's Comet came in, at that time it was not Halley's Comet, known as Halley's Comet. So basically, when that comet first showed up, based on the calculation of Mr. Newton's work, Halley actually predicted that the comet should come back in 76 years, and he gave it a date when it should appear. Within a day or two, it reappeared again. So that is actually something useful in the sense that we predicted something with it. So that's why Newton's work was accepted in general. It was accepted later on because it was able to predict the existence of Neptune. Neptune was never observed before that. There were two independent mathematicians who, based on the path of Uranus at that time, which was discovered by accident, by the way. So Uranus and there must be another planet, and that planet must exist in here, based on the calculations. So sure enough, when the first chance came in, and people pointed their telescopes, and there they found Neptune, planet Neptune. So again, this was the success of Newton. That's why the theory of Newton became acceptable, because it was able to predict something that was not observed before and then confirmed. Now, Einstein came to basically say everything that Mr. Newton did is correct, and he can predict everything that Mr. Newton actually did using the theory of Einstein, but that's not good enough. If all you do is just explain somebody else's work, that is absolutely unacceptable. You have to reject it. But he did something more, namely explain the path of Mercury, and well, that is a step up, but it's not good enough in a sense that all you did was explain something that we know. Maybe under some other circumstances it is not true. Like I said, he predicted other things, including the gravitational lensing that was observed in his lifetime. Black holes that are observed only a few years back. I mean, we knew about their existence. There was other evidence for their existence a long time ago, after Einstein basically passed away, but we knew about their existence. There were a lot of compelling evidence for their existence, but now we actually observed them. Gravitational waves also is another concept. There are so many concepts. The GPS system relies on his work actually to work. So a lot of things. So this theory is on solid footage and he has solid grounds. Again, the geometry that results from this whole thing has a problem. In a sense, this is a non-Euclidean geometry, really, that gives you the time dilations and all of these things. The Euclidean geometry, the one that we're used to, has if you have a triangle, for example, triangle, the sum of the angles inside is 180 degrees, no matter which side the triangle is. And triangle can only have one 90-degree angle. The other angles cannot be because the sum overall has to be 180. So if one of them is the 90 degrees, you cannot have the other two 90 degrees. The maximum you'll have is 190 degrees, and the other two, they add up to the other 90 degrees. So this is called the Euclidean geometry. There were two other possible geometries that need to explain this one, either, and depending on the density of the matter in the universe, either it's an open geometry where the sum of the angles inside are actually less than 180 degrees, or actually a bent geometry, and that bent geometry is the curvatures that we're talking about, so that the sum of the angles are actually more than 180 degrees. So it turns out we are in a space where the sum of the geometries is actually angles inside the triangle is more than 180 degrees, and this geometry has a name, actually. It's Minkowski space, and that is the one that that is used for this theory. The math for it, honestly, is very, very complicated, even for a so it's really not something that is good introductory topic in here, but this is the point in here. It has to do with the way things are. Here is the point I was trying to make in here. The sum in a Euclidean geometry, this is our daily experience, is exactly 180 degrees. This is the geometry that you have in here. As a matter of fact, you can have a triangle with the sum of the angles in here is 270 degrees. Each one of them is 90 degrees. Like, for example, on the surface of the Earth. You can have, if you take the entire surface of the Earth as a sphere, this is the case. And in the saddleback, this is like a less than 180 degrees. So this is the question that people sometimes, and this leads to the fact that the space-time is actually one structure, and that is bent, and it's bent because of the presence of mass. So now the law of gravity that we knew, g times the mass of the first object times the mass of the second object divided by the distance squared, is not needed. There is no need for a force. All we have in this case is just objects basically need to move fast and fast to avoid falling into the object. The object in here, because the space of time is being curved, and the curvature in here has to do with the amount of matter that it has in it. So that's why we are basically attracted to the Earth, because of this fact that we have to accelerate just enough so that we don't fall into the center that is created by the Earth in here, the center of this curvature in here. So this is an explanation based on geometry of the forces. Okay, gravitational waves, and I made the point that they're disturbances into this space-time continuum, basically, and this disturbances, they must occur with supermassive objects to be detectable. If you read about the LIGO, or if you had a chance to talk to some people who worked with it, you will see that actually the intensity is so small that you have to have the width of this disturbance is less than the size of the proton itself. It requires a lot of sensitive equipment and a lot of time and adjustment to really find a gravitational wave in here, because they're so small in intensity. Yet, as I was saying, we were able to find them. Okay. So again, this is everything for this chapter. And this is everything for your class. We're done.
Does that mean there's no more meetings on Thursday?
No more planned meetings, but if you guys want to meet, I mean, to discuss other things, either on a one-to-one basis or a group, it's fine, okay?
Okay.
But the content is covered. We covered all the content for this class. And the only thing that is left is the exams. The review should be made available for you. Actually, it's going to be available for you on Friday morning. And you take your time doing it. Please do it. Make sure you're ready for your second exam, and make sure you submit the assignments that are missing. And if you have difficulty or have questions, please let me know. I'd be more than happy to help you with your assignments to make sure that they are met and done and everything else, and you pass the class with flying colors. And unless you, I don't know what to say. So, okay. So here is the deal. First of all, I'm going to stop sharing the recording. It was a pleasure to have you guys in the class. and I will see you later on.
Yeah, thank you for everything.
Thank you, guys.
Yeah. Thank you for the lectures.
Thank you.
Thank
I'm
you.
gonna stop. Thank you, guys.
We're not gonna do the discussion board.
No, there is no discussion requirement for this ones or for several classes before. So you're not required to submit anything unless you have a question, which is you're more than welcome to do so. That's a good question, actually. There was another thing I wanted to say in here, and I know a couple of you have left already. Two things. First of all, tomorrow there is an event in the morning, a little after 4:30 in the morning until like 5:40 or something, until like basically sun up. What's going on is there is a lunar eclipse tomorrow morning around that time, because we are in the full moon for this month, for this lunar month, and actually it's going to be an eclipse, and it's really a nice event if you can wake up that early and take your binoculars and look at it or take pictures. It's really a nice event. That is one event. The other one is going to be in on October of this year. We don't have the exact date for it, and that is the launch of the James Webb Observatory, which is similar to the Hubble telescope. So this is a James Webb telescope, and it's much bigger mirror than the Hubble. So it's going to allow us to do a lot of observation of the universe and confirmation of these things and planets and things like that. So I want you guys to look for that event in October. There will be an event involving the STEM Center. I'm working with the STEM Center coordinator to have that. So I hope to have you guys there, at least to enjoy the day, discussions with other people, and maybe you're interested to see the questions, what is going to happen in terms of the exoplanets, potential of life on other exoplanets, and how this James Webb will help us understand all of these things and will help us see galaxies further than what Hubble did for us, and basically the wonderful stuff that we will learn. So I look forward to see you guys in October. Sounds good?
Yep.
Okay.
Okay, thank you.
No problem. So I'm going to stop the recording now.